Hello, everyone. Dr. Ross is with you for our first chapter lecture in this introductory general chemistry course or Chem 65 course. The contents of this short lecture are going to be as follows. We're looking at matter, so we'll give some definitions. We'll then classify matter or categorize matter according to the type of matter it is. We'll look at physical properties and physical changes, chemical properties and chemical changes. And finally, we'll finish up by a quick overview of the scientific method. So without further ado, let's begin. Okay, so some definitions. So looking at the left over here, we've got some basic definitions. What is matter? Matter is anything that has mass and occupies space. How do we know if matter has mass? Well, put it on a scale. If it registers something greater than 0, it has mass. If it occupies space, you can see it. You can't be in the same space as it because it's already there. So pretty much anything that you can see it because it occupies space. So that would be matter. And chemists study matter. So chemistry is the study of matter, energy, and their changes. So chemistry pretty much is the study of everything. And that's why, if you look over on the right side, chemistry is located central to many other disciplines. Chemistry is referred to as the central science for this reason. It has a very broad definition. It encompasses a lot of different things. So if you're a physician studying medicine, your patient has mass and occupies space. So really you're a chemist. If you are a civil engineer designing, what would the civil engineer design? Cities, I think. Maybe. What would the civil engineer? Let me quickly. Well, I think civil engineers study bridges, maybe. Anyway, I've just embarrassed myself. But some kind of engineering. So you would be a structural engineer. That's something I do know, the structure of things. If you're a structural engineer, whatever the object is that has a structure, has mass and occupies space, you are a chemist. So probably on the course to becoming these types of engineers, you've taken chemistry. Certainly if you're a physician or an allied health major or something like that, you have taken chemistry along your pathway to becoming an allied health person or a physician. Not only does this mean that most people have to take chemistry at some point, but interpreting that differently and leveraging it to your advantage, chemistry is very valuable because it allows you to spring off in different directions to pursue different opportunities. Now that we know what matter is, let's classify it. So matter can come in two broad flavors. It can either be a pure form of matter or a mixture. Let's look at mixtures first. There are two flavors of mixture, homogeneous mixtures and heterogeneous mixtures. Taking the homogeneous first, the prefix homo means same. So a homogeneous mixture is more than one material combined in a way that it looks the same. It looks uniform, it looks featureless. So for example, salt water is at least a mixture of some kind of salt and water, but the salt is dissolved, so you don't see the pieces of salt. Imagine going to the beach and you scoop in a glass some salt, some ocean water. It just looks like water. You wouldn't know there was any salt in there unless you tasted it, and you could taste the salt. So therefore, salt water is a homogeneous mixture. Wine is featureless, ignoring the fact that there may or may not be bubbles in it. Let's say there are no bubbles, which would be a feature, but just still flat wine is featureless. So that would be a homogeneous mixture because you don't see the alcohol, you don't see the sugars or any of the sulfites dissolved in the liquid. A heterogeneous mixture, on the other hand, the prefix hetero means different. So here it looks different to the unaided human eye. So homogeneous looks the same to the unaided human eye. Heterogeneous looks different. There are features. Those features could be anything that you can distinguish without the aid of a tool. A canonical example of a heterogeneous mixture is cereal with milk. For example, if you've got your Cheerios in milk, you can see the O's clearly distinguished from the milk itself. It's a feature, therefore it's a heterogeneous mixture. Slightly more disgusting example, because why not, is sewage. So if you imagine sewage, you've got particulate matter, you've got paper, other things, not to mention turtles and crocodiles and fish. No, but you've got particulate matter and liquid material, so that would be a heterogeneous mixture. Moving over to the left now, looking at pure substances, there are two categories. Elements, there are 118 elements in the periodic table. Any one of those would be considered pure, whether they're monatomic, so existing in isolation. The examples given here are sodium Na, or neon Ne, or any one of the other 118 elements. Diatomics, some elements prefer to exist as diatomic molecules. Here are the 7 diatomic molecules, but there are others as well. So for example, sulfur likes to hang around sometimes in a cluster of 8 sulfur atoms. So long as it is sulfur, only sulfur with multiple copies of sulfur in clusters of sulfur packages, that would still be considered elemental. Because if you were to fish your hand in and randomly grab a molecule out, 100% of the time it would be the same thing. So therefore it's pure. On the other hand, a compound can be pure, but it itself is a mixture of more than 2 different types of elements. So for example, water, the symbol H2O, that means there are 2 hydrogen atoms and 1 oxygen. There are 2 different types, hydrogen and oxygen. And although they're different, they've come together to form a unique form of matter, a water molecule or a water compound. And if you were to take a bucket of water, fish your hand in, randomly grab a sample, look at what you have, you would have only H2O. So there's no variance, there's no features, you just have H2O. So that would be considered pure, even though it's a pure compound rather than a pure element. Properties. There are flavors of properties of matter. We've categorized them here as physical and chemical. So physical properties are inherent characteristics of a substance. Examples given are density, melting and boiling points, and hardness. These, you can think of these as properties that you could measure without damaging permanently in any way the matter itself. So for example, you can measure the density, you can calculate the density of an object. Density is a ratio of mass over volume. So you could weigh an object, you could measure its volume, and you've done nothing to damage the object. You could repeat the measurement and still get the same density. You could repeat it again because you haven't damaged it during the measurement. So it's a property that you can repeatably measure. So that would be a physical property. Conversely, a chemical property is something that you have to alter the material in order to measure it. So for example, the flammability of gasoline. To verify it, you would have to burn the gasoline, and once you burned it, you can't do it again. Something that reacts with water. So for example, if you take an antacid and you dissolve it in water, it might dissolve and generate some gas. So if I say to you, a property of that antacid is effervescence, or the ability to form bubbles in some way, the only way to show you that is to actually release the bubbles, but I can't do that more than once. So that would be a chemical property. Physical and chemical changes. Again, this idea of reproducibility for physical, it's because it's a reversible change. Phase changes are reversible. So a phase is the state of the matter. So whether it be a solid, liquid, or a gas, that's the phase or the state. You can change from a solid to a liquid to a gas back and forth repeatedly without altering the material. For example, you could take solid ice, which is just solid water. You could melt it by adding energy. to make liquid water. You could add more energy to make gaseous water, so you could boil the liquid, and then you could condense the gas back to a liquid again. You could freeze the liquid back to a solid again, and you could go back and forth, repeating the process. But at the end of the day, you've still got water molecules. You haven't permanently changed anything. You could reverse what you've done. So what you've done is a physical change. Chemical changes, on the other hand, are irreversible changes. So for example, burning. If you take some wood, you set fire to it, you burn it, you cannot collect the ash at the end, collect the sound that was produced from the crackling flames, collect the light that was given off, collect the smoke, collect the energy needed to maybe cook your hot dogs on a grill. You can't collect all of that stuff, put it in a box, wave a magic wand, and produce wood again. It's an irreversible change. Something irreversible has happened and you can't go back. Aging is another chemical change. You can't unage. Age is a one-way ticket, unfortunately, at least for now. Okay, so now we've got these changes. We can exploit the difference between physical and chemical properties of matter as a separation technique. So for example, if we want to physically separate objects, we can use physical methods. And an easy way is just add a physical barrier. So filtration is one way. So if you were to filter your own coffee, you would add some filter paper, you put the coffee grounds on the filter paper, you add the water, only the water and the coffee goodness, all the coffee juices can go through the filter paper, but the coffee grounds cannot. They've been prevented by this physical barrier, and we've filtered the coffee. Distillation works in a similar way, but rather than size exclusion, we're using physical property differences like boiling point. So if we take two compounds, A and B, and let's imagine A has a lower boiling point. So when we boil the mixture, A is going to boil first. We could then collect that while what I say, A has the lower boiling point, so A would boil, B stays behind. We could collect A and B would stay behind, so we've effectively separated A and B. Chromatography, we probably won't do in this course, but you might have heard of it. Chromatography is separation of colors. So we probably the way you've seen chromatography in an everyday experience is if you accidentally if you accidentally wash clothes with a marker in the pocket, sometimes the colors in the marker's ink can separate. So you might put a black marker in your by your white shirt, wash it, and then you've got like a streak of red, blue, and maybe gray colors because the black marker is a mixture of all those different colors. We have ways to quantify that a bit more accurately in the lab. Chromatography is probably something you'll do more of in organic chemistry. Centrifuging or centrifugation is a way that you can separate based on mass. So for example, if you wanted to spin down a blood sample, you want the heavy platelets to settle and the plasma to stay up top, you can centrifuge it. If ever you've been on a I don't know if they even have them anymore, but like a merry-go-round, if ever you've driven around a bend at some speed, you feel yourself being pushed towards the edge of the car. That sense is essentially what would happen on a very small scale if you were to centrifuge. You centrifuge at very high velocity and everything gets pushed out. And usually a tube will tilt as it's spinning around. And so the outside of the spinning centrifuge becomes the bottom of the tube and all the heavier objects get pushed towards the bottom. Oh, I think I missed something. Yes, chemical separation techniques, again, similar to chemical changes. You have to permanently alter something in order to separate them. So let's say you have two chemicals, A and B. You can essentially chemically react A therefore destroying it and essentially removing it selectively from chemical B. So for example, if chemical A is thermally decomposable, you can thermally decompose it and render chemical A therefore pure. Okay, the last slide in this video is the scientific method. The scientific method is a way that chemists can do science, or any scientist can do science. This is the canonical Francis Bacon scientific method, or the Baconian scientific method. It is not the only way that we do science in 2023, which is the year that I'm recording this video. We have many, many ways that we do science nowadays. This is just a canonical way that you can do it. It's an oldie but a goodie. Notice it's cyclical, so we can cycle. Now, so if you imagine, before we look at the details, if you imagine a wheel, so this is cycles like a wheel. This wheel can either spin in place, kind of like the wheel of an exercise bike, so you can go nowhere. So you can make zero progress by spinning this scientific wheel. Or like a regular bike, you can get traction and you can move in a positive direction. The difference between the scientific method wheel and a regular wheel is a regular wheel can be wheeled backwards. I don't think the scientific method can go backwards, because anytime you use it, you either gain nothing, which is you staying in place, or you gain something. But I don't think you lose anything by trying to cycle through the scientific method. So first of all, you have to make an observation about the natural world, or notice something that's reproducible, like a law. And you get curious about your observation. You can make observations qualitatively. So for example, typically a qualitative observation has no units, like the color or an odor of an object. Or you can make a quantitative observation. These typically have units, so the length of an object, you can measure that. You can weigh the mass of an object, which has units. You can get the temperature of an object, you can get the conductance of an object, the concentration of an object, anything with units. And you can come up with an hypothesis. A hypothesis means something that's below a thesis. The prefix hypo means below. Thesis is, for example, a theory, a tested idea. This is below that. You've had no testing take place yet, but this is the seed that you are going to test to verify. So it's below a thesis. It's a hypothesis or a hypothesis. It's an educated guess. So what does an educated guess mean? It has to be reasonable. It has to be testable. So yeah, reasonable and testable. So once you've got your hypothesis, you can do an experiment. You can see if your hypothesis is confirmed or denied. And then you can cycle back and make more observations, develop a new hypothesis test, and you can cycle. Okay, I think that will do us for this video. So I'll see you in the next video.